Right, welcome to the Tribodynamics lab. You're probably wondering what tribodynamics actually means. This is a mixture of the sciences of tribology and dynamics. Dynamics, I'm sure most of you are fairly familiar with, the science of motion, of objects relative to each other. But tribology is the science of relative motion between objects, particularly where they're actually in close contact with one another, such as items such as friction, sliding friction between things, and of course the science of lubrication that goes along with that. Okay? Students will come in here mainly in part C and D of the programme, i.e. their third and fourth years, where we build on the engineering science learning that they undertake in their first and second years, and start work in part C on their major individual project, and also will work on experimentation to do with modules such as tribology, drivetrain dynamics, and dynamics generally. So what we'll do now is we'll go down into the lab and have a look at some of the student projects, lab work, and some of the research that we're involved in. This is a typical Part C individual major project. It's a nice balance of experimentation, the rig we see in front of us, and background modelling to actually model the phenomenon that take place. What we have is a cylinder head from a 2-litre diesel engine, a production car engine. And what we're interested in is looking at the frictional effects between the camshaft and the roller followers that we have inside there, and trying to minimise the friction between them. Because like everything nowadays, we're trying to improve the energy losses with any given system in a whole powertrain, be it a hybridized engine or a conventional petrol or diesel engine. So the project here was to model what was going on, taking into account the dynamics of the valve train system itself, the frictional effects, and modelling the tribology, i.e. the interface between all the sliding and rolling components inside the top end of the engine. So that creates a computer model and some data based upon the real data that we have for that engine. And then the thing that we'd like to do with all of these projects is then validate it. So we take the computer model and we compare it with experimental data. So in this case, the project student did the modelling and then built up this test rig here, which is the cylinder head, driven by an electric motor, with a torque transducer here and an encoder on the end, so that he can actually compare his modelled results compared with the real-world results of the actual engine in a motored form as opposed to a totally running form. So, in conclusion, what we get is a nice balanced project of modelling, experimentation and validation, which is very good for the skill base of the student looking to their further employment.
So one of the elements of tribodynamics and application areas that we look at within this lab as a focus for our research but also our teaching is transmission engineering. So we look at transmission engineering from high performance racing vehicles to off-road and also for on-highway applications. So I'll talk you through some of those examples. In the drivetrain dynamics module, which is a fourth-year module, we look at a noise, vibration and harshness issue which becomes apparent to passengers called gear rattle. The students conduct a multi-body dynamics analysis using commercially available software, and then they compare that with measurements that they take in the lab here to measure gear rattle and gear noise during operation, and then compare their results to the experimentation. And by comparing the two, then they can use a physics-based optimization strategy to choose ways of reducing that noise and vibration issue which can occur in vehicle transmissions. One of the third-year student projects that I have run in here as well is looking at wet brake efficiency for off-highway applications. So these wet brake packs spin, and they spin with a thin film of oil which is used to cool the brake surfaces. The brake surfaces are cooled, but it also causes a lot of drag, so we end up with this engineering paradox where we want to provide cooling, but we don't want additional drag, which would cause inefficiency of the vehicle. So the student project was to optimize the various groove geometry on the brake pack, to optimize heat transfer, but also to minimize the drag losses. So the student project also followed a combined experimental and numerical approach, generating a computer model in MATLAB, and then comparing the computer model with experimentation of a component level rig, which was the disc spinning between two stator plates. Again, comparing, understanding the physics of what's occurring so that they can make educated design improvements for the application. So the last example of a student project that we'd look at is ensuring the lifespan of transmission systems and the gears which make up those transmission systems. So when the gears come into contact, when they're very highly loaded together, or when they have very slow sliding speeds and very little oil is pulled into the contact to separate the surfaces, the surface roughness and whatever the surface is comprised of has a key role in how the surfaces wear. So one of the projects we looked at using the mini traction machine is to investigate how surface coatings and surface finishes could be used to reduce gear wear and improve the lifespan of the components. So the mini traction machine has an idealized geometry, so it's a ball sitting on the disc, and that can represent very similar contact pressures, and it can also generate very similar slide to roll ratios in the contacts. So then we can determine how a different coating or different surface finish would affect the wear, and then we can extrapolate that using models to determine what the lifespan of the gears might be in application.